So we are heading towards problem set 3, which is coming out tomorrow, where you will finally actually implement a proper epidemic model of SIR type, the type that, you know, the simplified version of the types that everybody has been talking about all over the media. And that's going to be exciting. And so there's one piece left to talk about that that you're going to be using, and that is, how do we define a custom type in Julia? And what is that? What is that useful for? What does that even mean? And you know, how can we actually use it to do something useful in a simulation? And you'll be applying that in the problem set that's coming out tomorrow. And so then we'll split the development of this model between tomorrow's problem set and next week's. So just a reminder that next Monday, the 20th of April, is Patriots Day, so there is no class, and there is no Tuesday scheduled, and so we just lose that class, and there'll only be one class next week on Wednesday, the 22nd. Okay, so let's so we just have, before we do custom types, we have this we have to talk about variability. How variable is a random variable, right? It's called a random variable because its values vary, its outcomes have some range of possible values, and so we want to know, well, how big is that range? So last time we introduced random walks and how to build up a simulation by simulating many trajectories, and we're going to use that right now, I guess. Well, maybe we won't actually use that exactly. And we looked at what is the difference between a vector or vectors and a matrix in Julia. So they're sort of conceptually the same. They have the information about the trajectory of many particles, but there are these two actual different data structures that we can actually change between using this hcat function, but they are different. Okay, so goals for today. So we're going to look at first how to summarize a probability distribution, and that's sort of separate. And then, that's the end of what we were doing last time. And then we'll start talking about, okay, well, how could I simulate different kinds of random walkers in Julia, with different kinds of rules for how they jump, for example. And we'll see why it's important then to write what we call custom user-defined types, our own sort of new types in Julia, and how to use that
David.
Write generic code. Yeah.
There's a question saying, are these slides posted yet? Maybe you could put them on GitHub for people to follow along with.
Yeah. I thought I had remembered that I had to do that, and then I got distracted. Sorry. Okay, they should now be up. Thanks for the question. And I've again lost. Oh, it's so annoying. I just lose when I change to a different window. I just lose the zoom window. It just gets hidden behind a lot of other windows. Okay, got it. Right. Okay, so how can we characterize the variability of a random variable? Yeah, so at the end of last time, we saw that if we have many random walkers, then we can draw a graph like this that we'll go and do it in Julia in a minute. So on the x-axis I have position, and on the y-axis I have basically the probability of being in that position. Right, so if we call the position sort of x, then we have the probability that the random walker position random variable x at time n, what is the probability that that is equal to the value x? And we saw that we have some distribution that looks something like this. So some kind of Gaussian bell-shaped distribution. Of course, actually what we have is not really that curve. We actually have just some data points because we only have discrete values of the position, right? That's not a vector. So position x takes the values, say -10, -9, up to 10, just integer values. So we actually have dots, but we sort of join them up with a straight line so that it's better, visually. And so that is the shape of the probability distribution, right? So let's recall the probability distribution is the collection of values of, let's say, all values, the probability that x is equal to n. So these are numbers and they sum to 1. So the probability over all n, the sum of the probability that x equals n has to be 1. That means that the particle has to be somewhere. And so that is, the definition of probability distribution is the collection of those possible values. And if we have a discrete random walker that's jumping around, we know that it can only have these finite number of outcomes between -n and n at time n, if it's just jumping a distance 1 at each step. And so, so this, we can also, so I'm using this word in this phrase probability distribution. We can also talk about the probability mass function. That's the function that, for sort of f of n equals the probability that I'm at that position. So there's two different concepts. One is a function that, given a value, gives me the probability of being at that value, and then the probability distribution is the collection, the set of all those values. Okay. So that's just, if you've taken a probability course, you've seen all these concepts. If you haven't, then I think a very nice, easy, intuitive way of understanding probability distributions is to do these simulations and say, oh yeah, okay, I see that, this number occurs a certain fraction of the time. I'll think of that as a probability. Okay. So what we now want to understand is, well, what is the shape of this distribution? So, well, like, where is it sort of located and what is its shape, and then how wide is it? Right? So we have to define all these terms and have a way of calculating them. So, in particular, as it says here in the slide, we see just from looking at this shape, we see that that these values cluster around a central value. And so we call that the expected value, or the mean of the distribution. And then we see that values near the extremes over here, we have sort of, it's very unlikely to be a position -10 at time 10. And so the probabilities are very low, and as we go further and further along, it gets increasingly unlikely to be far away. And so how far away, in general, do we end up is the question. Okay, so how can we calculate these things, on the computer? So one of the simplest things we want to calculate is the sample mean, or the average value. And so how do we do that? We just do sort of the standard calculation of the arithmetic mean of the data. So we have data points, which are the outcomes, right? So these are the results of running the simulation, results of simulation, which we run, some number n, capital N times. So the simulation is, simulate a random walk for time 20. That is one simulation. We're going to look at the final position of the random walk and then run that simulation or that experiment, run that a large number of times, capital N, say 10,000. So we get 10,000 data points, x1 up to x 10,000, which are numbers in the range from -20 to 20. And so we can ask, well, on average, where are they, right? So we can just calculate the arithmetic mean, which is the sum of the data divided by the number of data points. Okay, and so in Julia, we can do that with this mean function that's in the either the statistics or the stats-based library. So we can just load the statistics library and then use the mean function, or we can just define it ourselves, right? It's easy to define it ourselves. If we have a vector of data, sorry about the background noise. We have a vector of data. We're just calculating the sum of that vector, and then we're dividing it by the number of values in the vector, the length of the vector. And so, you know, I guess we've seen this sum function before in Julia. Of course, you could write that yourself as well. It turns out that Julia's sum function is actually going to be better than the one you write yourself, because, you know, it turns out to be actually surprisingly difficult to write a decent sum function for floating point numbers that, well, it takes account, you know, minimizes the floating point round off error that we're not talking about in this course. So Julia has this nice function, or you can just write it yourself. Okay, and then so that will give us the mean of the data, right? So the data is representing so when we do a sample, we get what's called, well, when we run the experiment a lot of times, we get what's called a sample, and that we are sampling from some sort of theoretical distribution that really exists, you know, in the abstract. And if you could run the simulation an infinite number of times, let's say, then you would get sort of the true probabilities. And so that's called the population. So we have this sort of population, which is this theoretical construct in the background, and then we're actually getting real data, which is a sample from that population. So what we're actually calculating here is the sample mean, the mean of the sample of data that we're calculating. And that sample mean actually approximates, we hope, the true mean of this distribution. So in particular, what would you expect? So let's, if you can answer this question over the chat, what would you expect the sample mean to be for our random walker? Okay, so we have an unbiased random walker. It's jumping right with probability a half and left with probability a half. We're going to run it for 20 time steps. We're going to say, you know, x20 is the position at time 20 of our random walker. And my question is, what is the expected or average or mean value of x20? Where would you expect the random walker to be? We have that, have answers over chat. So yeah, so somebody said 0. So we expect it to be 0. Why? Because, well, when we're adding all these values up, well, it's just as likely to be at position -3 as position 3. The other way around. Position -3 and position 3. It's just as likely to be at position -10 as position 10. So the probability of being at position -10, the theoretical probability is the same as the theoretical probability of being at +10. Okay, that's fine. But then, well, what about the actual data, you know, the actual value in the actual data? So, so we're going to do that in a minute. Well, I guess we'll just start doing it now. So can you see the notebook? Yes, no? Can somebody tell me if they can see it? Yes, great, thanks. Okay, so let's just remember how, you know, we had this function walk. We said how many steps it was going to take. So we started at 0, and then we have for I in one num steps, and then we just added this rand of, this is just exactly the same code as last time, right? So you can just go back and copy it from last time. We just add to x this random jump, either -1 or +1 with probability of half of each, and then we're going to return the final value of x. So let's just check that that works. So if I run it for a number of steps 20, then I get some value, and run it again, I get a different value, and I get a range of values. And so what are we going to do? We're going to sort of run an experiment. We're going to run, we give it the number of steps in the walk and the number of walks. What does it do? It just returns the data, which is run the walk for that many steps, that many times, right? So I'm going to use an array comprehension. We've seen this several times already. You should be, you know, this should be natural, becoming second nature to you right now, right? So I'm just defining a new function experiment. I can use this nice one-line syntax for defining my function. This is defining the function called experiment with these two parameters. And it's just calculate this array of data by running the walk a lot of times. So experiment, you know, none steps 20, we said, and then let's say 1,000 walks, and we're going to call the result data. And so it spits out this vector of values. So by the way, in Julia, if you use this apostrophe or quote, single quote, after a vector, it will actually give you the transposed vector. So I don't know if I mentioned that that is a very slippery concept that it took a long time in Julia to iron out. It turns out to be very slippery to define what you mean by the transpose of a vector and how it behaves. We won't enter more details, but it's just, right now I'm just using it as a cheap trick to save vertical space. Instead of printing out this vector as if it were a column vector, I'm printing it out as if it were a row. So this is just the transpose of data, which you can also write like this, transpose of data. So I'm just saying that quote means transpose. Or, yeah. Okay. Okay, so what did we do last time? We used statspace, which has this count map function, just because you are actually writing this function in problem set 2, so I'm not going to do it right here. We'll just use the one that's already defined, and you can use that to check that yours is correct. And that returns this dictionary, just like yours is going to do. And so we're going to call that counts, and then we want to plot that, right? So I'm going to load the plot package, and you're going to do it properly by making vectors of everything. But for now, we'll just make a bar graph of counts. So bar graph is something that only is valid when you have when you have a discrete set of data, and it just puts a bar on top of each value, and the height of the bar is proportional. Yeah, and I had forgotten that this is why we cannot use dictionaries for this purpose. You get this ridiculous result. So instead of that, we're going to use the histogram function. Okay, so we haven't talked about histograms because histograms are the equivalent of bar graphs, but for continuous data. So we're not really going to go into continuous data much in this course, at least not yet. So a histogram will make bins, which have a certain width, and it will count the number of data points that fall into each bin. So you see that by default, it chooses a number of bins, and I can just choose, I can force it to use some different number of bins, like this, bins equals 20, and then I get, I have some data, and it's counting the number of times each, what's going on? No, sorry, I don't want counts then. I want to histogram the data. Histogram the data. There we go. Yeah. So that's pretty, pretty equivalent to what you're doing. The difference is that I can actually give it a different number of bins, and it's lumping together several different values of n. So this is like position. Let's call it position x. Remember, X label bang will add an X label to the pre-existing plot. So this is a position, and it's saying, oh, between 0 and 5, there are this number of data points, right? So it's 400 and something lie between 0 and 5. So you could write this code yourself, of course. It just happens to already be written in this histogram function, which is in the plots package. There's a more sophisticated version of, or more accessible version of histogram in the statspace, I think, package. So let's just see how to use that. So we say fit histogram with a capital H as a type, fit histogram to data, and let's call that H. And what that actually gives me is it returns a histogram type with all of this data inside. So it chose edge widths, edge length, and it chose and it gives me the weights, the number of things in each of those bins. So these are the edges of each bin. So this is :5 means step length 5. So it's also doing the same 5 width 5 bins, and it's actually giving me the heights if I just use this histogram, a function in the plots packages just plots the data, and it's very difficult to actually access the data. If you want the data, you need to do it like this. Okay, so in particular, if you want to normalize the data, well, you would have to extract this weights object, which is h.weights. That, well, as we'll see in a minute, that extracts the field called weights from the object called h. And then we could, divide it by the sum of h.weights. That will normalize it, and then the sum of that result will be 1, and that's their now probabilities. If I'm using the histogram function instead, I can actually do the same thing by giving it an option which is normed equals true. So if I do 40 bins, because I know that I'm going from -20 to 20, then it gives me something like this. And so now it's telling me that this column, this bar, goes from 0 to 1 now, at least approximately. Actually, it's not quite right. But it goes to 3, 4, 5. Oh, yes, right. Yeah, from 0 to 1. So that's all the ones with value 0. So yeah, it's a bit annoying that it's shifted. It's not exactly over the 0. Whatever. Let's not worry about it too much. And you can see that there's these regions where there's nothing as well, right? So why is that? Because in the original data, if you look at it, there are no odd numbers. Why are there no odd numbers? Because after an even number of steps, I can, because I'm always jumping either left or right, I can only be on even positions. So that's called a parity question. Parity is even or odd. So we can see that we can never be on odd numbered points at an even number of steps. Okay, so that's what the data looks like. And yeah, this normed equals true actually normalizes the data. So now this is a picture of a probability distribution. This is what I called the probability mass function, right? It's just drawing the probability mass function. The height at each number is the probability that I got that number, the relative frequency that I got that number. Okay. So you're making a function that does the same thing as histogram, except it does it specifically in the case where the data is discrete, right? As I said, histogram works also for continuous data where you can have values, outcomes of any real number. And that's the definition of a histogram. So the point about a histogram is that you can have bins that are actually different widths. And so then the area of the bin, the area of the bar actually represents the total number of points that are in that bin, in that width. But in this particular case, because the bars are all the same width, that means that actually the height is proportional to the value. Okay, so that's what the distribution looks like. And now we want to find the mean, right? So because I already loaded the package, I now have this mean function available, but I can define it as I showed. I could do the same thing to do sum of data divided by length of data, and I get 0.116 as well. So the mean of this distribution is 0.116, whereas we were expecting it to be 0. Right? So it turns out that it's not exactly 0 because we have some finite amount of data and it just happened to be slightly more on that side than on that side. And so, but still 0.116, if I draw it on that, on this figure, it'll be very close to 0. It's basically, basically at 0. So you can say, well, how far away, if I run this experiment, how many times did I run it? 1,000 or something? If I run this experiment 1,000 times and I calculate the mean, you could ask how far away do I expect the mean to be from the true mean? So that's called the error of the mean. And I don't really want to go into that right now, but basically the error of the mean, yeah, okay. So before we get there, we have to go to the next stage, right? So the next stage is, so we did the mean. Now what else? The mean is, is not enough, right? Because the mean could be the same if I do this distribution that I did, or I do one that looks like that's much more close together, that doesn't spread out so much. So what I need to measure as well as the mean is how much it spreads away from the mean. Okay, so spread away from mean. So how am I going to calculate that? So I have some data, and now what am I going to do? So can we have answers in the chat? So I don't just want a word, right? There's a word that describes what I'm going to do. I don't want that. I want to know, what do I need to calculate to find how far away I'm spreading from the mean? Yeah, so instead of raising your hand, just add, just write in the chat, please. Yeah, so somebody said the variance, okay, but so that's what we're going to end up calculating, but what does that actually mean? What are we actually going to calculate? What are we going to do to, you know, we want to see how, we want to calculate how wide this distribution is. What do we need to do that? So anybody want to, average squared error from the expectation, average distance of each value from the mean, exactly. Distance from the mean at which the probability drops below a certain point, could do that. Yeah, width at half mean. Okay, yeah, these are all good answers. So yeah, basically, so let's just, oops, what happened? Don't know. Okay, so we have, let's just draw the data again. There it is. So now we want to, you know, I could put the mean on with this V line. So just mean of the data inside these square brackets. You know, I told you that this, you need a vector for V line. And so some people are having trouble with V line in the homework. I really don't know why. I can, so I don't know what the solution is. So I'm just going to put line width equals 3 and line style equals colon dash. And I'm going to hide the legend because we don't want that. And then it's actually pretty hard to see that with those colors. So let's put color equals, does purple work? Yes. Okay, so you can see hopefully this purple thick dashed line, that's the mean. Now we need to know how far away are we from the mean. So yeah, so all of the answers were, you know, pretty correct. Basically, what do we want to do? We want to see how far away is the data, right? So this is measuring how far away the data is, or we could just scatter the data. And what we want to measure, so then let's put a horizontal line at the mean. This graph with the same profile, so line width equals 3 and line style equals dash and color equals purple. And there is the mean, right? And now we want to know on this picture, well, on, you know, some measure, some way of measuring how far away from the mean we spread out. So we could just take the maximum value that we reach on each side. That is a measure of how far we spread out, but that seems wrong, right? Because like this value, I mean, it's a perfectly valid value that came out of our experiment, but it's somehow an outlier, right? It's somehow kind of, yeah, we don't really want to count that. We want to know where the majority of these values lie. And so it's going to be some width, you know, around here, somewhere around 5. That's like, oh yeah, that's sort of where most of the values are. So the first thing we're going to do is, okay, we're going to actually center the data. So that's called centered data is going to be, so I want to subtract the mean. So it's also called demeaning. I'm going to subtract the mean from each value of the data, each entry in this vector of data. How would I do that in the chats? How do I subtract the mean from each data value? Anybody? The chat just keeps disappearing. Can use the dot, yeah. So I'm going to do an element by element. I want to do the same operation on each element. So I'm going to do dot minus will subtract element by element, right? And then dot minus equals will actually, center data equals data dot minus mean of data. Okay, so you could, yeah. So I always worry about whether this is calculating mean of data at each iteration, like each step through. I presume it's not. Does anybody know about that? I mean, if you're worried about that, you can just do it beforehand, right? Mean of data, m equals mean of data, and then just point-wise, element-wise, subtracting m from the data. Okay, so then we have some new data called centered data. And now we're going to plot that. So we can just take this same graph and plot it, scatter of center data, and mean of center data. And of course, the mean of the center data should now be exactly 0. And right, so if we just calculate it, mean of center data, we should get exactly 0. Yeah, so it's 0, within floating point error. So this e minus 16 means 10 to the minus 16. Right? So 1 e minus 16 just is notation for 10 to the minus 16. Okay. So, that is, again, this floating point, using floating point numbers. 10 to the minus 16 is about the size of the smallest, well, the difference between 1 and the next. So if you do, there's a function called next float. So the next floating point number after 1.0 is this one. And the distance of that from 1 is this number 2 times 10 to the minus 16. That's called machine epsilon. And it's basically, you can think of it as, sort of, in some sense, the smallest sort of unit that you can distinguish in floating point calculations. So that's a whole topic that we're not going to go into, but it's just useful to know that 10 to the minus 16 is sort of this magic number when you're using double precision floating point numbers. Double precision, that means float 64. That's the name double precision comes from, a previous era when people used to use mainly 32-bit floating point numbers, and nowadays we usually use 64-bit floating point numbers. Except, on GPUs now everything's changed. Okay. So now we have our center data. So now what can we do with the center data? We want to find the average of the center data, right? But I just did that and I get exactly 0. So that's no use. So what can we do instead? So I want to know how far away is the center data. So how do I calculate the distance? Well, it's some kind of absolute value, right? So I need the distance. Let's call it the spread is the absolute value of the center data. Right, so that's like, how far away am I? So let's call that abs data is absolute value. So how do I apply the absolute function to each element of the center data? Again, I use the dot, abs dot of center data. So now let's plot that data, scatter of abs data. So now that is all, of course, bigger than 0. The absolute value is always bigger than 0. So basically it's just like folding up this picture. I took this picture and I folded up the bottom half onto the top half. And so now they're all positive, and I just sort of copied all of those points on the bottom and put them on top of the points on the top. Not on top, I mean, wherever they fall. And that gives me this picture. And so now I am close to being able to say, well, how far away am I? Well, I could take the mean of this data, right? So I'm going to take mean of abs data. That gives me 3.59. Let's plot that. So mean of abs data. And color equals purple. So there is the mean of this data. So that is a measure of how far away it goes. Of course, looking at this picture, it doesn't seem like a very good measure. But let's ask the question, well, actually, how much of the data lies between there and there? So, so how much of the data lies between there and there? How am I going to calculate that? Can you answer that in the chat? What proportion, so it's difficult to, this picture is actually quite confusing because these dots are like kind of on top of each other. So actually we can use, so I'm not sure I've mentioned alpha equals 0.5. If I add that as a plot option, that will actually make my dots transparent, except, no, not in the H line, sorry, in the scatter. The dots are now transparent and you can see that they're overlapping, and there's like a lot of dots right here, and it's kind of hard to see that when you just draw them all solid. reduce this alpha value and they get even more transparent. So how can we check? How can we actually count how many points are between 0 and the mean, for example? Can you answer that in the chat? Okay, no one's writing. Okay, so actually maybe can I do breakout rooms here? No. Q&A. What was the syntax to call the absolute value again? Abs. Abs is the absolute value. Yeah, somebody answered, thanks. Okay, there we go. So there's somebody wrote in the chat what the solution is. So so I have abs underscore data is the absolute value of the data, and I want to check, is that less than, is that between 0 and, in other words, but it's all positive, so is it just less than the mean? And I want to check that element wise. So let's call now M is the mean of abs data, and I want to check abs data is that less than the mean M, and I want to, so that will give me, as usual, a vector of booleans. Will tell me for each value in the set, in the array, in the vector, is it less than M or not? 1, yes. 0, no. And now I want to know how many of those there are. And so, so in the chat, Hayden suggested using sum. You could use sum, but it's sort of more intuitive to use count. We're just going to count the number that are less than M. There are 491. I need to divide that by the total number of data points. So length of abs data. And so I get that 0.491. So about half the points are less than the mean, right? So, okay, I captured where half of the data is. So, but maybe I could say, okay, instead of using one mean away from the one mean away from 0, I'm going to use 2 means away from 0. So I could say how many are less than 2 times M. And by the way, you can, in Julia, if you have a number like 2, you can actually write 2M instead of 2 times M. Only if it's a literal number like 2, not if it's you can't do this if it's a variable like X. And I could just write this, it gives me a nice, it looks more mathematical if I just write 2M instead of 2 times M. So what proportion is this in 2M? 0.889. So if I do 2M instead, 2 times, so you can't, I could write 2 mean here, but then it's confusing, so I'll just put 2 times mean. And then, oh yeah, that actually captures most of the data, right? Okay, so you may be wondering why we use the absolute value and not the squared error, as some people said, right? So this is giving me the average value, or 2 times the average value, the average absolute distance. So this is a perfectly valid measure of how wide a distribution is, and actually it's more robust than using the square. The square, what will the square do? Well, if I have these big values over here, like 15, when I square that, it's going to be, because I'm squaring it, it's going to be much bigger than when I square 10. It's going to be sort of disproportionately bigger, actually. So you're actually giving too much importance to the values that are more extreme. And so using this, just the absolute value is actually, in some senses, more useful. But the classic thing to do is to do exactly the same calculation, but instead of doing this absolute value, you just do the square, right? So instead of using the absolute distance, we'll do the square. So like squared data is take all the data and you square it element-wise. So I can write that like this. Data dot hat 2, that's squaring all the data. And now I'm going to plot that. Look at what that looks like. So people don't usually even plot these things, right? But I think it's important to plot it to get a lot of intuition. So squared data, what do you call it? Alpha equals 0.5. And you see that, yeah, indeed, as I was saying, well, that really sort of, a lot of the stuff is concentrated now, very close, much closer to the origin than these extreme values. So the extreme values are being given more weight. Okay, it's just a choice. Maybe that's reasonable. Okay, so now we're going to do the same thing. So we've got squared data, and we can say, well, what is the mean of the squared data? So let's call m equals mean of the squared data. And we could plot that. We're not going to do that. And then we want to know how much of the squared data is less than the mean. And the answer, and divided by the length of the squared data. And the answer is 0.73. So actually a lot more of the data is now concentrated less than the mean. And so this is one of the reasons that actually using this variance is useful. So yeah, so the mean of the squared data is called the variance. So I was supposed to square the distance. So m is the mean of the original data. Then when I square the data, what am I squaring? I'm actually squaring the data with the mean subtracted and then taking that element by element square that. And then let's call m2 the mean of that new data. And so I want to calculate the fraction that's less than that other mean, that new mean. This is called the variance, right? So that's what the variance actually means, right? So often people just sort of teach it as this is what you calculate, but this is what the variance actually means. It's the, sort of the mean of the width of this scaled version of the data. Okay. Okay, great. So again, I can say, okay, instead of M2, I'm going to take 2M2, and then I find that there's about, am I doing this right? Yeah, I think so. There's something like 90% of the data. So we didn't actually take very much data, right? So maybe we should take some more data. So what do? Data equals run experiment. It was also because we only took 20 steps. So let's take 50 steps and 10,000 runs. Even though we take 10,000 runs, it's still almost instantaneous to run it, right? Remember, you can do at time. It'll tell you how long it took to run. I mean, it's nothing. So I could do, 1,000,000 runs. So you could just write 10 to the 6, that's 1,000,000, and it takes 0.3 seconds. That would take 50 times longer if I were running it in Python. And so you would be sort of sitting there for a few seconds. Okay, so this is much more reasonable. I'm getting sort of 67% less than the one mean, and so this is not giving you the right number. Am I doing the right calculation? This is, no, I'm not doing the right calculation. Sorry, this is not correct. This is, sorry. So what I want to be calculating is, okay, so I find this variance. Yeah, okay, I see. So I find this variance, and the problem with the variance is that I now squared everything. So if you think that these data are measured in meters, for example, then when I'm squaring it, I'm getting a quantity that's a number of square meters. And so I can't actually compare that to the mean, for example, which is in meters. And so I need to take the square root. And so this is going to be called sigma. So as we mentioned, if I type \sigma and then I type tab, it actually gives me this sigma character. I'm going to make that the square root, which I can do by \square root tab. That just gives me a square root symbol and square root of squared data, right? So let's actually call this variance. So variance is that, so square root of variance, sigma. Oh, come on. Sorry, this is the mean of that. Yeah, the variance is the mean of this thing, and now sigma is the square root of the variance. And now what I want to look at is how far away from the mean in terms of sigma are we? So I want the data, and I want to say, how far away are we from the mean? So I'm going to subtract the mean. Well, and so what I want is basically m minus 1 sigma is less than data is less than m minus sigma, m plus sigma. So I actually chain these comparison operators in Julia, by the way. And so I can do this. And now I want to do that for every element of the data. So again, I can put dot, a dot less than, and dot less than here. And so that gives me now a vector of all of the elements which are between that value and that value. So by the way, if you don't like these dots, of course, you can just do an array comprehension, right? So you can just do sort of m minus sigma less than x less than this for x in data. And that'll give you the same answer as using the dots. So broadcasting minus dot less than x will give me exactly the same result when I put data, the actual vector. And then I want to count the number of them that are between there and divide by the length of data. That is what I'm supposed to be calculating. Yes. How many of the original data are between there and there? So if we scatter the data, come on, alpha equals 0.5. And now I've got a lot of data, so that's a very bad idea. Let's interrupt that. So let's just do the data. That's called reduced data. Is data from 1 to 10,000. Just going to select those parts, that part of the data, and I'm just going to scatter reduced data. It still takes a little while to draw 10,000 points. What's going on? Why is this not giving me anything? What? My notebook is all messed up. I can't do anything. If I do that, it doesn't do anything. This is very annoying. I'm gonna restart, I guess. I can't even restart. Yes, I can. Okay, sorry about this. That's very frustrating. Okay, let's go back up top. Experiment. I don't need stat space, I need plots. Okay, and now M not defined, mean not defined using stat space. Okay, so I get 68% within one standard deviation. So let's visualize that. So scatter reduced data. Let's call it just data 2. There's data from 1 to 10,000. I'm going to scatter data 2. It still takes a while. Oh yeah, because it's compiling. This is the first time I'm plotting. Okay, so Shashi said I just had to wait, so I was too, okay, maybe 10,000 is too many. Let's just do 1,000. Okay, there we go. That's too few. Okay, 5,000 points. So now we can plot the mean, H line at the mean. 3, color equals purple, line style.
I couldn't find that in your music.
Come on. Sorry. Yeah, so you see, if I forget to give that I need to give it a vector, it gives me this cryptic error that's difficult to understand. And if I give it a vector, so that just seems to me ridiculous. Can somebody raise an issue? Shashi, can you raise an issue about that on plots, or I'll do it later. I should be able to just give it a number, and that should just work, in my opinion. Okay, so there's the mean. And then now I know the standard deviation. I'm going to actually add that into these H lines, right? So M plus 1 sigma and M minus 1 sigma. It's going to draw lines at all of those points. And you can see that, yes, indeed, we are at, so I could actually draw those in different colors, I think, if I give it different, I give it a vector of colors. No? Oh, it's a shame. That's a bit ridiculous. Okay. Who knows what's going on there? They apparently have to all be the same color. That's disappointing. Okay, so you can see that, oh yeah, indeed, sort of a big fraction of the data looks like visually it's between there and there, and I actually know what fraction it is. It's like 68%. And then if I do the same thing and I do it with 2 sigma instead, then I see that, oh yeah, now almost all of the data is inside that range, right? So, and what is the fraction of data that's inside that range with 2 sigma now? So from minus 2 sigma to plus 2 sigma, it's actually 0.95 or 0.96. So it's 96% of the data is between 1 mean and plus or minus 2 standard deviations. Oh yeah, so I didn't say that sigma is called the standard deviation. Right, so we're calculating deviations from the mean, and this is the standard way to do it, if you like, is you square and do all this thing with the squaring, but we could do this sort of absolute version of the deviation instead. So Dan Siegel says that from data science, people have this sort of idea that if you use the absolute value, you get what's called the L1 norm, and that prioritizes the bulk of the distribution in layers. And that corresponds to what's called a lasso regression, whereas the mean squared error is the L2 norm, which prioritizes outliers. And that corresponds to a ridge regression. Okay, thanks. Okay, so that's how we can think about and visualize the width of a distribution. And then I should come back to this error of the mean, standard error of the mean. So what is that? So, if I have n data points and I calculate the mean, but the n data points sampled from the same distribution, then what should I expect? So, so we're basically, what does that mean? It means we have some number of steps, say 20, and we have some number of times we want to run the experiment, say 100. I run the experiment, that meant that number of steps and that number of times, I get some data, and I calculate the mean, and I get something that's of size 0.4, when n was 100. Now let's multiply n by, so this is some distance away from the true mean, which is 0. Now let's multiply n by 10 and calculate the mean. And I see that I get something smaller. If I run those experiments again, of course, I'll get different values, right? I get 0.26 and I get 0.1. I get 0.22 and I get 0.02. But you see that in general, I get a smaller value as I would expect. The mean is closer to the true mean when I run it more times. And so the question is, well, how far away are you from the true mean? So that's the standard error of the mean is actually given by the sigma of the distribution, which I can actually calculate with the STD function in stat space. I think this is a terrible name, but that's what the name is. Standard deviation, right? STD, ST for standard and D for deviation. Okay. I don't understand why you can't just be called standard deviation, but there you are. So, okay, it's not even defined. So maybe I'm wrong. Maybe it's not called that anymore. Anybody know? Stood error? No. Stood error? No. I've totally forgotten what, I'm totally blanking now on the name of this function. Maybe it's in a different package.
Did you load in statistics?
Yeah. Yeah, there it is. Standard. It's called STD. Yeah. STD, question mark, STD, compute the sample standard deviation. Yeah. Okay, thanks. Standard deviation of data. Let's call that sigma. And then to get this standard error of the mean, well, what is the mean? So the mean is given by, x1 plus x2 plus plus xn. So what you have to do is calculate, well, what is the variance of the sum of all of these things? So that will tell me the width of the distribution. And then you're calculating the mean. So you're dividing that by n. And so you have to work out what that does to the variance. So you go through all of this in a statistics course. So we're not going to do it here. And the answer is that the standard error of the mean is the sigma divided by square root of n. Square root of n. Right, so n in this case was 1,000, and when I run it, I get all of these values. And the standard error is supposed to be 0.13. So what that means is if I run this thing a lot of times, so I'm supposed to be doing this data, collect this data a lot of times. So I'm sort of running a meta experiment. Well, whatever. Yeah, I'll just run it a lot of times. So data is run this thing a lot of times and calculate the mean of all of those experiments, right? And do that a lot of times. So let's say 1,000 times. So there's my sort of meta, my mean data is the mean from each running all those experiments a lot of times. And now I'm going to calculate the mean. I don't know, am I doing the right thing? Sorry, I'm getting confused. Yeah, I think so. Mean of mean data. No. No. Variance of mean data. Standard deviation of mean data. Yeah, there we go. So that number is supposed to be the same as this, right? It's the standard error. It's not quite the same because there's a factor that comes in that's a bit strange, but it's basically that, right? So, and when I calculate, and when I increase n, of course, like if I run it for 10 times longer, or let's say 4 times longer because there's a square root, I'm going to run it for 4 times longer, I should get a standard deviation that goes down by a factor of 2, and I do. Okay, so that tells me, that gives me, it's basically I have a distribution now, right? I can plot a histogram of the mean data. These are all the means that I get from running the experiment a lot of times. And I get a distribution that's very narrow now, right? It only goes from -0.2 to 0.2. And it has its own mean, which is of course near 0, but it also has its own width. So there's standard error of the mean is just the standard deviation of this new distribution, which is the distribution of all the means when I run it a lot of times. Okay, so basically, these are concepts that come up in your probability or statistics course. And if you don't do it by running these experiments on a computer and visualizing, I mean, I think, I personally just never understood like what the point was or what was going on. But if you do it numerically, you really understand what's going on with these concepts. Okay, so let's take a little breather and we'll just, so it took longer than I was expecting, but we'll just start off on defining new types and then we'll carry on with that on Wednesday. Okay, so defining new types in Julia. So there's some slides about this, but I'll just, you can go and read the slides. It'll just recapitulate what I'm going to do here. And yeah. So what do I mean by defining a new type and why would we want to do it? So if we have a random walker, I like the example of random walkers. I think it's very intuitive. So, what I could do is say, oh yeah, okay, so my random walker, has a position. Let's call it X, and it starts off at 0, and then, later on it moves. Okay. And then if somebody asks me, okay, now make another random walker, I'll have to make one called X2, I guess. And then X2 is going to move as well. And then I could actually make a vector of random walkers just like we did, and it would just be like a vector of numbers. But now suppose that each of those random walkers, so those random walkers, they're integers and they're going to jump by integers. And now I want another kind of random walker, which is going to jump in a different way. So let's call it Y. It's going to start off, it's going to be a floating point value, and it's going to jump by just adding, some random number from a Gaussian distribution. So I can generate that like this. Of course, now we have the skills to check that that's doing the right thing. We can do histogram of, let's generate 1,000 of those random numbers, and then we'll draw a distribution of their values. And we see that indeed it is generating values that come from some random Gaussian distribution using. So this uses some, complicated algorithm that we're not going to go into how you actually do this. But what we've actually seen is, well, I could actually do this just by simulating a few random walks as well. So if I want to generate a Gaussian distribution, I can generate an approximate one at least by simulating random walks. And this is using a better algorithm called the ziggurat algorithm, which is, you can look up. So for Gaussian distributed random numbers, or normally distributed random numbers. So you can generate all kinds of see that also the distributions.jl package has a load of probability distributions. If you need to generate a probability distribution with this particular behavior, it's probably already in this distributions.jl package. Okay, so because that's a different type of random walker, right? It has floating point values and it has jumps where I take the jump distance as just I sample it from this random this Gaussian distribution. And so, well, but okay, so I want to be able to talk about when, I want to be able to write code that is generic. So how can we write generic code? So what does that mean? It means a single function, a single walk function, right? To generate a random walk. But I want it to be that works with both of these functions, that works with discrete and continuous distributions. So one way to do that is I actually make different functions. So I could make a discrete jump function. What does that do? It just takes my standard rand of -1 and +1. Okay. But then I want a continuous jump function. What does that do? It just takes one of these Gaussian random variables, which is centered, has average 0. It jumps left and right automatically. Okay. So there's two different jump functions. And now I want to write my walk function, just like I did before, n steps. Right. So I start off with x equals 0, and then for I in 1 to n, x plus equals the result of my jump function and return x. Okay? But now I want to make a version of this function that works for both my discrete random walker and my continuous random walker. So can you think of a way to do that? So there's a question for the chat. How could I modify this function so that I could use either of these two types of random walker? So then, basically all that's different about them is this jump function, right? And I want to sort of tell it which one of these I want to use. Yeah, so somebody said, put jump as an argument to the function. So one of the things you could do was just use an if. You could say like, I wanted function walk and then type, like walker type, and then sort of if walker type is equal to the string discrete, then blah, 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 right? This is what you would do in many languages. This is a really terrible idea, so don't do it. Why? Because there's something better you can do, which is, as Tanner said, I'm going to actually send in jump as an argument to my walk function. So this is, I'm passing a function as an argument to my function. In many languages, this is kind of hard to do. In Julia, it's just as easy as writing the name, and then so now this jump here, instead of calling some function that I defined earlier, right, that was called jump, it's actually going to call whatever function I passed in as the argument to this function. Okay, so that's great. So now I can do walk of 20, let's say 10 steps with discrete jump. So I just pass in the name of the function as the argument, and I run it again, and it keeps giving me 0. But no, okay, it is actually doing a random walk, and it just happens that okay, let's do more steps. Yeah, it's getting away from the origin, right? It's sometimes at the origin, but often not. And I can walk with the continuous jump as well. And then what is that going to give me? It's going to give me a continuous, a real value as a result. Okay, so that's the first sort of generic code that we've written, where we, useful code, where we actually have exactly the same function, but it has two, it's doing different things by passing in this function as an argument. But there's a little wrinkle. What is the little wrinkle? Can anybody see a little wrinkle from this piece of code with these, what's coming out of here? I mean, it works. It's giving the right answer, but there's something weird. Can anybody see what it is? The return types are different, exactly, yeah. Float versus integer. So, when I'm calling this discrete jump, it's returning an integer. When I'm calling the continuous jump, every step it's returning a float. And yet, this x that lives inside this function, by the way, starts off as an integer, right? And so then when I add, when I call this jump function, if I'm calling the discrete one, it's okay. I just have integers everywhere. But if I'm calling the continuous one, what happens, x was an integer, and now it becomes a float. So it's actually changing type. And so if you run, okay, maybe this is not, I don't know if I should do this. Let's try. So I'm going to time, using the benchmark tools package, I'm going to time each of these and see which one's faster. And so the discrete one did 20 steps in 125 nanoseconds. That's really fast. The continuous one took a bit longer. So I'm actually now not sure if that took longer because it's, adding floating point numbers is more expensive, or because this x is actually changing type. And so basically in Julia, to get good performance, you do not want things to change type. Okay, so there's some problem because we need to tell it what the initial value is as well, right? So, okay, so I could add, I could make a new version where I actually had to pass in an initial value, right? So I could pass in an initial value and just say x equals x0. And then I just have to be careful, x walk continuous jump, I actually have to tell it, oh, I have to give it a continuous jump value. This feels a bit clunky, right? Because I know that this continuous jump has to be associated with a float, and this discrete jump has to be associated with an integer. So there's something kind of, it feels like there's what you could call a code smell. There's some issue about the code that I'm not being able to solve, which is that I have to pass this extra information, and it feels wrong to have to pass that information. So what is the solution for this? So the solution is that we have not actually told Julia that there is this concept of discrete random walker, right? Nowhere in the code is there something called a discrete random walker that has behavior, that has properties that I can talk about or tell Julia. So that's what I need these types for. So, hello, sorry. Yeah, so let's say custom types or user-defined types. And in Julia, they're called composite types. Many languages have these. Many languages like Python and C++ are what's called object-oriented programming languages. Julia has objects, but it is not an object-oriented programming language. It has what you could call objects of some user-defined type, just like other languages, but it is not a typical traditional object-oriented programming languages. Okay, so let's see what it is. So how do we define a type? So we're going to define, something called a discrete. So I'm going to call it my discrete random walker, because in a later on we'll call it something. We'll call discrete random walker something a bit slightly different. So we'll say my discrete random walker, and we'll put this word struct. And then that's going to have an x, which is of type integer. So this is a type annotation. It means that x is declared to be of type integer. So we haven't really used types until now. Suddenly, you don't really have to do that. Yeah, okay. Let's just do it. Okay, and then, okay, so what does that actually do? So that makes, so this is where it would be useful to be able to draw. Can I do that somehow? Yeah. I guess I can just use the annotation here, draw. No. No. Yeah. So it just makes like a, oh, come on. Just make some kind of box. And inside the box, there is some data. Here's one bit of data, here's another bit of data. In this case, there's only one bit of data, X. But so that's what it makes, a box with some data inside. And that box is called a my discrete random walker box. It's a box of that type. So basically what I'm declaring here is the structure of that box. What does that box look like? It's like a template for that box, a cookie cutter for that box. I haven't actually made any random walkers yet. Okay, so I'm going to clear that annotation. And now I'm going to somehow get out of annotation mode. Yeah. Okay. So that's what it is. It's a box with data inside. We haven't actually made a random walker. To make an object of this type, we call a function with exactly the same name. So, you know, remember that you don't have to type out this stupid long name. You can just press tab and it'll also automatically complete it for you. So my discrete random walker, I can actually use it if I just ask it what it is. It is not very helpful, but I can just use it as if it were a function, and I can give it a value, right? And then if I call that something, W for walker, this is, you know, what is W? It is, I can now say it is an object of type my discrete random walker. And not only that, it has inside a value, which is 10. And I can access that value by putting W.x, right? So W.x is Vx inside, you know, the variable x that lives inside the object. So this is what an object is, object W. So an object is like a variable with a particular type. And it has fields inside. So X is the only field that lives inside this object, and I can access its value like this, W.x. Great. Now I want to move the walker. So how do I do that? I do W.x equals W.x plus 1, right? Or something. Okay, so I need that in a separate line. And now I have a problem. So it says set field. So when I'm trying to change a field, that calls a function called set field, but I have an immutable struct. So by default, when I write struct, it gives me an immutable struct. So I cannot change the things that are inside the object of that type. So actually what I want to say is it's a mutable struct. And I would love to be able to write mutable struct and just redefine this type. But in Julia, you cannot redefine types. And so I'm going to actually call it my discrete random walker 2. Sorry about that, but let's just do that for the moment. Okay, and then if I do W as my discrete random walker 2 of 10, now I can actually move the walker, right? Great. So what I could do is define a function that moved a walker, right? So let's call that jump, but actually it's going to modify its argument. So we should call it jump bang, right? And jump bang is going to act on a walker of type my discrete random walker 2. So this is how I declare the function. Jump of that equals take the x inside W and add rand of -1 and 1. Okay, so it looks a bit strange in that format because I have this equal and then that equals, and it gets a bit confusing. So maybe we just should write instead in the long format function is exactly the same, but it's just maybe slightly less confusing, right? And then maybe we want to return the object W, right? So again, what does this do? It takes a W. So what does this syntax mean? It takes a W of type, right? Takes an argument of this type, my discrete random walker 2, right? Okay. So if I have this W, it's at position 11, and now I'm going to make it jump. So this is like, you could say, you know, how do I read this? It's like jump, please, right? It's like a command. You're commanding the walker to jump. Jump, please, W. And now W has changed, you know, what's inside has changed. So W has jumped. So we're mutating the object W. Okay, and then how do I write a walk function? Well, I'm going to do function walk. It's going to take n steps. So it's going to modify its argument. So W needs to be some walker object. And I could restrict this to only work with my discrete random walker 2. So this is, it needs to take an object of this type, random walker, my discrete random walker 2, and an n, with a number of steps. And so now I don't need a starting position anymore, because the starting position is actually stored inside this object, right? So I'm just going to run the simulation for I in 1 to 10. Please jump random walker W, end. And that's all it does. That's the whole walk function now, right? Because all of the interest is happening inside W. Of course, you could want to maybe return the whole vector of all the positions where the walker was during the, the trajectory of the walker. So let's say that it starts at 0. Okay, but that's a bit annoying, because when I'm defining this thing, I actually have to pass it, a position where it's going to start. Isn't there a way of just saying, oh, why don't you just start at 0 if nobody tells you otherwise? Well, what is my discrete random walker? You can think of it as just a function. My discrete random walker 2 is just a function. So you can actually define a method of that function that takes 0 arguments and takes no arguments. How do I do that? I do it like this. My discrete random walker is my discrete random walker 2, and I tell it, oh, okay, you're going to start at 0. So this is creating an object, my discrete random walker 2, the constructor function, you could call it. And it needs an argument usually, because it has to fill in this value that lives inside this structure. It has to fill that in with some value when you create the object. And then what I'm saying is, here's another way to create the object. This is called an outer constructor. Outer because it lives outside the class definition, the type. Sorry, don't talk about classes in Julia. Outside the type definition. You don't use the word class ever in Julia. It's a different concept, right? Because classes in other languages contain functions that do stuff. In Julia, you never do that. You cannot even do that, eventually, right? This function, in other languages, you would put this inside the type definition. Here, it's just another function that lives in the world, but it acts on these objects. Okay, so this is creating a new method of this function. How do I know that? Because methods of this now has 3 methods. Why does it have 3 methods? Because I should have done it before I did this. It already had 2 methods actually. So that's, basically there's an automatic conversion that it tries to do as well. That's what the other method is. And now I've added this one with no arguments. So if I just do my discrete random walker 2, W is this with no arguments. Now it generates one that's automatically at 0. And if I do W2, that generates a different one, right? So if I make W walk 1 step, then W moved, but W2, of course, is completely independent and it did not move. So inside W, there's a variable called X. Inside W2, there's a variable called X, but they're different, right? They're different variables X because they live in different boxes. They just have the same name, but well, they don't really have quite the same name. One of them is called W.X and the other is called W2.X. Okay, so we've run out of time. So the point is, now I want to, so now I know how to define this object that has some internal state, which is its position. I can talk about what is a random walker object. What does it mean to be a random walker? It means you have a position. And it means now that there is some functions that are going to be able to act on you, right? That know that they can take random walker object and do stuff with them. Okay, and so next time, well, we're gonna start off by defining a continuous random walker as well, and see, well, how can we make continuous random walkers walk as well? And in particular, this function walk actually should not care what kind of walker it is, right? This should work for any walker. Any random walker is just does a sequence of jumps. So if you can define your continuous random walker and then define jump for that, this function should actually be able to work for that as well. And that's what we mean by generic programming. Right? We want to write the same code, but have it work for different objects that do different things, right? They jump in different ways. So that's what we'll do next time. It's pretty exciting. So you'll need that for the homework. So the homework will come out tomorrow, but some of it you won't necessarily know how to do until Wednesday. Okay, thanks. So see you on Wednesday. Good luck with finishing problem set 2.